Sorry about that. All right. So, which is better? High contrast or low contrast? So there's not really a maximum or a minimum, but we think about it more as optimum. Okay, so an intermediate level, which results in an adequate range of exposures to the IR. So there's differences in signal, right, that create the differences in brightness levels that represent all of the tissues and a sufficient difference between the areas to distinguish them one from another. In other words, if all of the brightness levels are the same, then we're not going to be able to tell anything about that image, right? Or if they are either black or white, that again is we're going to lose information, right? So the key is an intermediate level, not too high, not too low. So you can look at this picture and sort of see what we're talking about there. You don't want the contrast so low that you lose information, or so high as in so which one is the highest contrast? Let me ask you this, the one on the top or the one on the bottom? On the bottom, C. C has the highest contrast because there's greater difference in those brightness levels. So think about your vision. With too little light, details cannot be seen. So think about when, this is a perfect example, when we're all walking around in the dark, right, over the past 10 days because we didn't have power, and you catch your toe on the corner of the furniture or something, right? That's because that was a detail that you couldn't make out. That's not fun, right? Or think about when you come out of a movie theater. So you've been in a dark movie theater and you come out to the bright daylight, how your eyes are just overwhelmed by that light and you miss things. You can't see certain things. So you don't want it too high or too low. With digital imaging, there are different algorithms and software functions that adjust the contrast or have an effect on the displayed contrast. And when we say the displayed contrast, we mean the actual on the display monitor of the image. So on this, and we're not going to get into this a whole lot right now, back in or next semester is when we really get into the digital concepts about what is the computer actually doing. When we talk about the computer fixing our image to make it look the same, remember we've been talking about that. So we'll get into this a lot more then, but you can just know for right now, you can see that what happens is there's something called a lookup table that's applied to the original information. So the image on the left would be that original data that's coming across. And then after the lookup table is applied, what has happened to the contrast on the right? Has it gone up or down? It's gone up because the image on the left is very low contrast, right? It's all the brightness shades are very close together. On the right, now there's more difference between the brightness shades. So there's more black and white than there was in the image on the left. So one of the ways that does that, just briefly, is let's say, for example, and we don't talk about, that's why I sort of have pulled back on this a little bit, because we don't start the intro to digital until the end of this semester, but every single pixel in your digital image, so just like your pixels on your television screen or pixels on your phone, every single pixel has a number assigned to it, okay? So it has a value. Every pixel has a value. And let's say, for example, in your original information or data that comes across, a value of 40 and 30 are applied to those pixels, as you see on the left there. Once that lookup table has been applied, now everywhere that there was a 40, there's a what? It's been reassigned to what? 90. And everywhere there was a 30, it's been reassigned to. So is there not more difference in the values on the right than there are on the left? So we would say that contrast has increased because there is a greater difference between those values. And what we're going to learn is those values represent a shade of gray. Okay, so So sort of like is represented there, the 40 and the 30 are sort of close together, shades of gray, and how the 90 and the 10 are now much further apart. The 90 is blacker, the 10 is whiter or brighter. So we'll get into that more towards the end of the semester. Again, manipulating the display contrast on a digital image, we can vary the contrast by using the window width tool. So you can see on our monitors that we can actually adjust the display contrast, just like you can adjust the display contrast on your televisions or whatever. We'll get into that more towards the end of the semester, and a whole lot more next semester, more than you want next semester. So a minute ago, I said that, we could add the word subject in front of contrast, and everything that we used to say about display contrast and film contrast still holds true when we talk about subject contrast. So subject contrast, the definition is the difference in radiation intensity between the various portions of the remnant beam after passing through the patient. So let's talk about a couple of words in that definition to make sure that everybody sort of follows what that's saying. So what did we say the word intensity means in radiology terms? What is intensity referring to? Quantity, amount, how many, right? How many photons, okay? So we're talking about the difference in quantity between the various portions of the remnant beam. What's the remnant beam or the exit beam?
Radiation after it goes past the patient.
Right. What is left over after it makes it through the patient? Okay. So subject contrast is talking about the difference in how much is left over after it passes through the patient. That's what that definition is saying. And it's caused by the differences in the composition of the patient's body parts. So we're going to look at these three different things that change the amount of radiation that makes it through the patient's body. So whether we're talking about tissue density, atomic number, or part thickness. So we're going to look at each one of those individually and talk about how it makes a difference and how much makes it through. So this is a definition. Subject contrast, that's a definition that you've got to know. So that first part of that is subject contrast. Then we talk about attenuation. So attenuation is the reduction of radiation intensity or quantity due to either photoelectric absorption or Compton scatter. So we've said that in general, there's three things that can happen, three fates that an X-ray photon can have, right? One of them is that it can do what?
Be absorbed by the IR or scatter or...
Well, be absorbed by the patient. So it can photoelectrically be absorbed. It can be Compton scattered. It can interact, lose energy, change direction. So that's the second thing. What's the third thing? Pass through. Yes. Pass all the way through, transmit all the way through without any interaction. So that's basically the three things that can happen. When the amount or the quantity of radiation decreases, that is the definition of attenuation. So attenuation is loss of intensity due to either Compton scatter or photoelectric absorption. That's what attenuation is. It means you have less than what you started with. Okay, so you have a certain number of photons being directed at the patient, and then you have a certain number that actually make it through the patient, right? So that loss of intensity is due to the photon either being absorbed or scattered. Okay, another definition that you've got to know. Here's one more. They all go together. They're all like a part of the same concept. Differential absorption is quite simply exactly what is in the word. It means that tissues in the body absorb radiation differently, and that is determined by the average atomic number, how compact the atoms are in the tissue, that's the tissue density, and how thick the part is. Okay, so Tissues in the body absorb photons differently. That is what differential absorption means. So when we look at these three things individually that affect, attenuation or affect differential absorption, which affects subject contrast, right? They all sort of affect one another. Atomic number, if you think back, if you had Ethan's class, and you certainly had this information in there, or, in your prereq courses. But remember that atomic number is the number of protons, which should equal the number of electrons in a stable atom. Higher atomic number yields greater attenuation of the beam due to absorption. So again, your higher atomic number structures are going to have greater attenuation because there's a greater chance that the photon's going to be absorbed. Okay? So a large difference in atomic number of adjacent tissues yields high contrast. I think I have, an example here. So for example, bone has an atomic number of about 13.8, lung has atomic number of 7.4. So this is going to yield high subject contrast because there's greater chance for absorption in the bone due to the higher number of electrons in the atoms just available for interaction. There's just a better chance because there's more electrons out there, right, that could have an interaction. So when you have something like bone and lung, so you think about the chest, right, and you have the ribs and the lungs, that naturally has high subject contrast, right? Because there's a big difference in atomic number between the bone and the lungs. Everybody following? Okay. So the second thing that affects attenuation or subject contrast through differential absorption is tissue density. And so we say that tissue density means how compact the atoms are to one another. Are they very compact, or are the atoms sort of spread out? So the greater tissue density yields greater attenuation of the beam. Again, there's just more atoms in there for possible interactions. So we say that a large difference in tissue density of adjacent tissues yields high contrast. So again, when there's a great difference in the atomic number, that yields high subject contrast. When there's a great difference in tissue density of adjacent tissues, that also yields high contrast. And here is an example of the tissue density. So again, if you look at lung and soft tissue, so the picture on the left is supposed to represent the atoms in, say, lung tissue, and the picture on the right is supposed to represent soft tissue. So you can see that they have about the same atomic number, but they differ in tissue density. So the soft tissue is more densely packed. There's just more of them per unit area. Does that make sense? So when you look at it, if those blue arrows are supposed to represent the photons, do you see how that there's less attenuation with lung tissue than there is with soft tissue? There's more of a chance that the photons are going to make it through the lung tissue than the soft tissue. So that means there's going to be less attenuation, less loss of intensity with lung tissue than there is with soft tissue. Right? Everybody got it? Okay. Sure, I'm staying on track with time here. So the third thing is anatomical part thickness. So simply talking about how thick the parts are, all right? Physical thickness. So as part thickness increases, there is greater attenuation of the beam. And that just makes sense, right? If there's more tissue there, then that means there's greater chance that an interaction is going to happen, right? Your odds are better, okay? So if you look at this picture, the picture at the top is if you have just 5 centimeters of tissue thickness, let's say that there was just this first layer down here, then you still may have a few photons make it through because it's not that thick. But if you double that thickness, then you can see that the number of x-rays at each level that actually make it through changes. So you can see this hypothetical, of course, but let's say there's 100 x-rays incident upon that tissue thickness, and you can see that it drops from 100 to 50 and then say 50 to 25 as the tissue continues to increase, the thickness of the tissue. I think I have another slide here that I hope will help maybe clear up part thickness. So if you look at this image, you can see that the yellow arrows are supposed to represent photons, okay? And the pink step wedge, okay, you can see it. This would be like looking at a step wedge on the side, all right? So as the thickness of the step wedge increases, what happens to the number of photons that make it through? It decreases, right? And you can relate that. Now, I know this is an old term right here, so just disregard this. This is an old picture, but I really like the picture. We don't talk about density anymore, and that was with film. That was a film term. So just disregard that. I meant to actually crop that out so that it would not confuse you. But you can see that the number of photons that make it to the IR and represent a brightness level, it changes, right? As the number of photons that reach it changes. So very dark areas of the image mean what? Did more or less radiation make it to those areas? More, right? So that's something you're going to need to understand for the test that you're getting ready to take for this week. Receptor exposure, blacker areas of the image mean more receptor exposure was incident upon that area. So as there are fewer photons making it through, because this part is just thicker, right? Then the brightness level is getting brighter and brighter and brighter as you go along. As fewer photons are made. So again, think back to the marshmallows, that marshmallow picture. The really dark areas, the marshmallows that are really black, I mean, they were exposed more to the fire. So you can think of it that way too with imaging. The darker areas, the blacker areas were exposed more to the radiation. Those marshmallows that are completely white had very little exposure to them at all, if any. The whitest of the white means that no exposure was there. So that means that no photons made it through to that particular area on the image. Okay, so the greatest difference, so what I did was I took the two extremes of that image. The greatest difference in tissue thickness yields the most subject contrast. So the thinnest to the thickest, if you compare those two areas, thinnest and thickest, that's going to give you the highest subject contrast. Does that make sense? So the good news is all three of those things, let's see if I have it. Okay. All three of those things that we said, atomic number, tissue density, and tissue thickness, because there's a difference in density and thickness, if there's greater difference in those, then that means you're going to have the highest subject contrast. So the greatest difference in atomic number, the greatest difference in tissue density, and the greatest difference in tissue thickness give you the highest subject contrast. Again, subject contrast being what? The difference in adjacent tissues. Yes. So, and subject contrast comes from the subject, the patient, right? Subject contrast is created by the patient. So the patient's parts and thicknesses and you know, disease processes and all those kind of things are going to affect subject contrast. That's the contrast you get from the subject, from the patient. Okay, and this slide is just to help you sort of, again, have a visual of differential absorption and attenuation. You can see that you know that those terms, radiolucent and radiopaque, we learned from the very first week. Radiolucent meaning what? What does radiolucent mean? Do the photons make it through or they don't? They make it through. Things like the X-ray table have to be radiolucent because we want the photons to make it through. We never got anesthesia, did we? Sorry, it just struck me that we were still missing a couple. So on this image right here, you can see that it's starts with air on the left and it sort of moves through as how the brightness levels would change based upon that particular part. So you can see that air is going to produce very dark brightness levels, right? Because a lot of those photons are going to make it through the air. What about that surgical pin? We classify that as being what? Radio opaque, right? The photons are being absorbed in that metal of that surgical pin. So in that area of the image, are photons making it through or not? No, they are not. So this is just sort of to give you, bone would be the next, right before surgical pin. So again, those really bright areas, like especially around the rims of the bones, you can see like right here. So those are going to be areas where, and along the edges where photons are not making it through because of the atomic number of the bone. So the controlling factor of subject contrast, so is KVP. That is going to be the controlling factor of subject contrast, the contrast that is produced from the patient, okay? So KVP, we already know, determines the energy of the photons. It determines the penetrating ability of the photons. We've talked a little bit about these things. It changes the differential absorption characteristics of the part, meaning it changes how or if radiation is absorbed by the part, because the KVP affects what? The ability of the photon to penetrate the part. So it also affects the amount of scatter that is produced. So all of these things are the reason why we use KVP to control subject contrast. Now again, with film, subject contrast and display contrast were the same thing. Are y'all following me? With film, the subject contrast was the display contrast. With digital imaging, the display contrast is based on what? The computer, right? We can make it look however we want it to look. So you don't have that visual that we had with film. I think I actually have, okay, yeah, have a video in there. Hopefully it'll play. If not here, then you can, I'll make sure that you can see it. That's something I did with film a while ago. This image right here, I just wanted to back up. You can see that these parts right here are exactly the same, right? This is two little step wedges that are exactly the same thickness, same part. Do you see how the number of photons that make it through changes because of the KVP? Does everybody see that? So do more photons make it through with higher KVP or lower? Higher. The higher the KVP, the more penetrating ability that photon is going to have. So the more chance it's going to have to make it through the part. All right. So this is just an example of it's called a penetrometer. We used to use them a lot to help prove these things and demonstrate these things, but not so much anymore. But I can show you one in lab. I believe I brought one over. But a penetrometer is just a step wedge. So darn it, they keep taking the pins out of here. So this would be like this from the side. Okay, is everybody following? So like a set of steps that you're looking at, this would be looking at the set of steps from the side, and this would be looking at the set of steps from straight on. Okay, so you can see how the subject contrast changes based upon the KVP that is set, right? Let's see here. So what is happening to this, and this is very important, these next few things that we're going to talk about is very important, that, and we're going to wrap it up here at the end with a sort of a summary page about descriptors and because you have to be able to talk about subject contrast in a number of different ways. All right. So what is happening to subject contrast as the KVP is increasing? You can see across the top, as the KVP is increasing, what is happening to subject contrast?
Decreasing.
It's decreasing. So what kind of relationship is that? Inverse. So as KVP goes up, subject contrast goes down. All right. Let's talk about why that is. Does anybody want to give it a shot as to explain why when KVP goes up, subject contrast goes down, meaning the brightness levels are getting what? Closer and closer and closer together. Why is that?
Based off the penetration of the X-ray photons to the IR.
That's right. So the penetration is becoming more uniform, right? As the KVP is going up, the part is becoming more uniformly penetrated, which means the brightness levels are doing what? Getting closer and closer and closer together. So on the image on the right, the thickest, first of all, which end would be the thickest end of the penetrometer? Top or bottom would be the thickest? The bottom, right? What did we say about the marshmallow? The very white marshmallow means no exposure, right? So do you see on the left at the bottom, that would be the thickest part because there would be very little, if any, exposure that made it through that thickest step. Is everybody following? So on the left, you basically have, I wish I had my pointer in here. On the left, you basically have about those right there are pretty much the same shade. We can tell very little difference between those. So we're looking at maybe 1, 2, 3, 4, and all of these are basically maybe 5 shades at 40 kVp, right? But we can almost make out all of these. Well, looking at it here, about down to there is still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can make out 12 different shades at 120 kVp. So which one has longer grayscale? The 120, right? The 120 has longer grayscale, lots of shades of gray, right? Low contrast. You're going to remember that. The LOs, low contrast, long grayscale, lots of shades of gray. If you can remember that, then you can just do the opposite for sure. So high contrast means short grayscale, which means few shades of gray or more black and white. Now, what you don't want to do is get the KVP confused. Which kind of KVP gives you lots of shades of gray, long grayscale, low contrast?
Higher KVP.
Yes. So don't throw in low KVP in that because that's not true. When we're talking about low contrast, lots of shades of gray, long grayscale, we get that from high KVP because it's an inverse relationship. The higher the KVP, the lower the subject contrast. Okay. This again is just another visual. I don't know if it will be helpful or not. You can see the difference when you go from 30 to 100 keV. The difference in the number of photons that are actually going to make it through and how that varies the brightness shade that is assigned to that area. Okay, so I don't know if that one's helpful or not. This is a video to help us understand how subject contrast changes with changing KVP. Let's see if it's going to play. It may not. Oh, yay. Okay. All right, so let me just explain a little bit. And I don't know, let me see. It can come up just a minute. I hope I don't blast y'all's ears out. So I did this several years ago when we still had some films. And so you can hear me describe, and can you, I know it's a little bright in here, anything, but can you see the difference in those two images that are hanging on that view box? Okay, let's see. All right, so see how with film, you could actually see it. You could see the difference in the subject contrast when you hung them up side by side. The only difference in those two images and the way that they were done is one of them was done with 106 kVp and then a certain mass, which we're going to talk about next week, that relationship. And then the one on the left was done at 68 kVp. So low kVp compared to higher kVp. That's the only thing that was different. But look at how it affects your subject contrast. Do you see the difference, especially like in this area right here? Y'all see that? How bright that area is? Why? Tell me again why that area is brighter on the image on the left than it is on the right.
Lower K.
Lower kVp, but why did lower kVp make it look like that?
Less photons are making.
Yes, because it's not penetrating that area as well. That's your SI joints. That's a thicker area of your pelvis. And so that area right there in a good bit portion of the spine there is just not being well penetrated at all. Those photons are actually being absorbed. So they're not making it through to the IR. So the subject contrast has changed when the only thing we changed was the kVp. Does that give you like a visual of what, because subject contrast, without this, is just something you sort of have to imagine, right? But with this image, go back to this. If you start to get confused about subject contrast, think about the only difference in the way these two images were created was in the kVp that was used. So higher kVp of 106, y'all like that 0, that was a washer, that's how I could find. So 106 was the kVp, and so it's much grayer. If you could actually see the films, and if I still have them somewhere, I may have them somewhere, I don't know. We had to get rid of a lot of stuff. But you could actually, really see how gray that image was compared to the image on the left. Okay, so let's move on here. Okay. And here's the actual images. I took a picture of them, and you can sort of see the difference in the, especially in the edges of the bone here around the SI joints, in the edges around the, now these are fake bones. This was a fake bone span instead of the real bones, but anyway. Okay. Move on here. So scatter radiation is produced when the primary X-ray photon interacts with an atom and changes direction. So it loses energy, it changes direction, so it's no longer going to give us an accurate representation of the anatomy. Scatter that hits the IR is unwanted and is called fog, and it always decreases contrast. Now, I don't want y'all to assume that low contrast is bad, because it's not. It depends on what you're looking for. Okay, so we typically like higher contrast for things like extremities and lower contrast for chest and abdomen. So when I say that it decreases contrast, decreasing contrast is not always a bad thing, but if contrast is decreased because of scatter, it is. Scatter always reduces contrast because it puts like a fog across the entire image. Hello. So, this chart right here, again, is meant to sort of bring all this material together and help you, organize it in your minds. So if it's something that's very radiolucent, that means that photons are making it through very easily. Those areas are going to be black. Those are going to be areas like gases and air. And then the opposite of that, the very radiopaque areas are going to be your whitest of white is going to be created from metals being in the image, like prosthetics, things like stretcher rails. If you leave a stretcher rail up or a wheelchair rail up, and contrast media. So that is where we're going to head here in just a second, is contrast media. How do we use contrast media to help us see different areas that are maybe really, really low contrast areas, and we wouldn't be able to distinguish structures from one another without it. Again, just another visual of how brightness levels represent different areas of the body and what kind of subject contrast that creates. So you can see that which of these two body, compositions would give you the highest subject contrast. Which two? Yeah, lead and air. That's the extremes. So that is going to give you the absolute highest subject contrast, because lead is not going to let photons through at all, and air is going to let a whole lot of photons through, right? So that's going to be your blackest and whitest areas, which would be the highest subject contrast. So contrast media. You haven't been to clinic yet, so you don't know a lot about this once, and you aren't going this week either, but you're going to get out there eventually. But you're going to see that sometimes we have to give patients what we call contrast media so that we can see areas that are very low contrast and areas that we would not typically be able to see without it. So giving a patient contrast increases their subject contrast. It helps make parts visible that are not visible under normal imaging of the area. So when you look at this image on the left, this is a KUB of a child. And the reason we can tell it's a child is because epiphyseal plates have not fully closed yet. You can see here in the hip joint and in the pelvis here that those epiphyseal plates are still open. So that means they're open so they can continue to grow. But we can't really see much about the intestines at all on that image on the left, right? It's just all very low contrast. Abdomens are inherently low contrast because the structures, the organs in the abdomen are very similar, right? So what they have done on the patient on the right is they have administered contrast media. All right. And so now we can see where the small intestine is, right? Right here in the middle. We can see that this is the large intestine or the colon coming around, and then here's the rectum here. So typically we can see a little bit of air here on this side. Y'all see that? That's air. We can see a little bit of stool, but everything pretty much looks the same until you put that contrast in there. And then it looks different. The most common types of contrast media are going to be air, iodine, and barium. Those are the three most common. So air occurs naturally a lot of times in the intestines, stomach, intestines, colon. But we can also introduce air as well to help outline things like the colon on double contrast VEs. And iodine we typically use for patients that when we are iodinated contrast is for sorry, I'm losing my train of thought here. For venipuncture type of administration of contrast. So when we're looking at things like the kidneys, where we want to see the collecting system, ureters down to the bladder, we can inject contrast into the vein. It goes into the bloodstream, and immediately within a minute, generally you can start to make out the nephrogram or the shadows of the kidney. And then within 3 minutes, generally you can see the collecting system. By 7 minutes, you can usually see in a normally functioning urinary system, you can see the ureters all the way down to the bladder by 7 minutes. That's pretty incredible. So the breaking up the types of contrast media, you have positive and you have negative. So your positive, let me see here. Okay, so I'll break it down. So you have your positive has a higher atomic number, higher mass density than the organ and structure that you're trying to see, and negative has lower. So let's look at that. So you can see in this image, this is an image of a shoulder. It's called a shoulder arthrogram. So arth meaning joint, gram meaning picture. So it's pictures of the actual shoulder joint. And so you can see that contrast has been administered. Some iodinated contrast has been administered in there, as well as some air, so that we can see the different areas of the joint space and see if there's any tears or anything like that. Negative contrast media shows as areas of decreased attenuation of the beam. So it allows X-rays to penetrate the organ more easily. So when you add air into a colon, it works sort of like a balloon. So it expands the colon out from being compressed down on itself. And so we consider that to be a negative contrast media because it shows as areas of decreased attenuation, meaning more of the beam can get through those areas because now they've been expanded with air. So those areas for negative contrast media are going to show up as very dark areas. Think about your lungs, right? And how lungs show up on the image. Well, y'all don't officially, just pictures is all you've seen so far, but you're going to see that in clinic. The positive contrast media is going to show up as areas of more attenuation of the beam, meaning we're going to have a greater loss of intensity with positive contrast media because it's going to absorb a lot of the photon. That's why they're showing up as areas of very, very bright areas, like the stomach. So this patient has been given barium to drink. Anybody ever had to have a contrast study before where you had to drink barium? No? Well, that's good. You did? It's nasty, isn't it? I used to make y'all taste it when I was the clinical coordinator at Greenville Memorial. I made everybody taste it because if we're going to be giving patients stuff to drink, we need to be able to tell them what it's like. And it's not awful. It's sort of like drinking a Maalox. If anybody's ever taken Maalox for like indigestion, you know, it's real chalky. So anyway, now this chart right here is going to help you sort through again what all we've talked about today. So we have descriptions of contrast. So we talked about with high kVp. So think back to that image of the penetrometers with all the steps, the different step wedge. High kVp means the photon energy is going to be high, which means the penetrating ability is going to be high, which means the subject contrast is going to be low, and the grayscale is going to be long. So low contrast, long grayscale, lots of shades of gray comes from high kVp. Low kVp means the photon energy is going to be low. There's going to be lower penetrating ability. subject contrast is going to be high and the grayscale is going to be short. So just like the higher KVP creates a more uniformly penetrated image, meaning there's more photons making it through, so it's going to be more uniform looking, which means the brightness levels are getting closer together, which means contrast is lowering. The opposite holds true for low KVPs. So low KVPs mean that parts of the image are not going to be penetrated. They're going to be very what? Bright, right? Very bright, because those photons are being absorbed. So it's going to be more black and white, right? Because there's greater chance that those photons are just going to be absorbed because they don't have the penetrating ability. They don't have the quality needed to get through that patient's part. So they're just going to be absorbed. So it's going to be a more black and white image rather than more grays. So again, high KVP, high photon energy, higher penetrating ability. Lower KVP means lower photon energy, lower penetrating ability. The end. That's a lot, right? But is it making sense? Okay, so do you see why we don't want to? We know that KVP, we're going to know really well after next week, but KVP does affect receptor exposure. We know that, but do you see now why we don't want to use KVP to control receptor exposure? Because it changes a lot of other stuff, right? It changes penetrating ability and quality of the beam, and therefore the subject contrast. And so it's changing things that we don't want it to change necessarily. So that's why we use mass to control receptor exposure. Because, and this is good review for the test that's coming up this week. Does mass change anything else other than receptor exposure when you adjust it? No, it doesn't change the quality or the subject contrast. It doesn't change distortion. It doesn't change spatial resolution. It only changes receptor exposure. So that's why we want to use it to control receptor exposure. All right, so do you have questions related to the test that's going to be open this week? Yes.
There's gonna be math on the test,
Oh, yeah.
so we can use blank of paper and then pencil and calculator.
Always. For all of my tests, you can, as long as you show it to me in your scan, your room scan, show me a front and back of a blank piece of paper. You can always have a blank piece of paper and you can always have your calculator. I think I have that in all of the instructions, but just in case it's not there, you can have a blank piece of paper and a calculator. You definitely need both of those. Well, some people might not want the blank piece of paper, but I would. I like to write stuff out. What other questions?
So all on the exam is gonna be the mass stuff, the inverse and what's the other one?
Exposure maintenance formula.
Exposure maintenance, what else?
So it's going to be the PowerPoint on receptor exposure that we did like 3 weeks ago, I believe. The receptor exposure, that was just the general, what is receptor exposure, that information. So, you know, how does MA time mass affect receptor exposure? What kind of relationship is that? And then the next week was inverse square law and exposure maintenance formula. So you need to know those. You need to know how to use those formulas. You need to know how to plug in numbers to use those formulas. Know how, you know, the whole concept of changes in distance affects what primarily? The change in distance, what we've been talking about. What does a change in distance affect? Intensity. I didn't hear what you said.
EXI.
Well, it does, yeah. And EXI because of intensity, right? So intensity is what's changing when the SID changes. And so because of that change in intensity, that means we have to change mass if we're going to compensate and keep receptor exposure maintained, right? Go ahead.
So I'm sorry, so the relation between the SID and the mass, directly?
Yes. So her question was, the change in SID and mass is a direct relationship, and that is correct. Meaning if SID goes up and you have more SID, then you need more mass to compensate. Because intensity went down, right? So because of that loss in intensity, we have to beef up our mass to compensate for that so that we have more quantity. Because we're losing quantity because of the change in distance. Yep. And so, let's see, what else was I gonna say? Any other questions that y'all have about the material?
For tomorrow, we going to have a different article,
Yes.
so we're gonna be still doing math, everything.
Oh, yeah. Mhm. You're gonna do math from here to eternity with my class. There'll be
And you say you
formulas.
posted on Blackboard,
Say again?
you say you post some example on Blackboard.
Oh, yeah. Yeah. There's, additional practice problems on Blackboard with the answers. There's also problems in your lab manual with the answers, so you can practice those. What else? Still have about 7 minutes. Okay, just make sure that you do the review questions. Those will be a big help to you. I've got to finish looking at the course outline and figure out RadTech boot camps and all that stuff. We said nothing was due. So nothing was due last night. We'll figure out when to make those due. I would say you need to do the RadTech boot camps before you take the test. So if you have not done them, do them before you take the test.
Do you remember like some of the names? Because I was trying to look back at the manual, but I'm kind of confused on the weeks now.
I am too. I am too. It's gonna be, so if you look at the, in Blackboard, under the, that first week start here folder, it says welcome and course schedule or something. There's this nice 1-page schedule that's in there that's gonna be changing, but it has them listed. And so like for the material for this test, it's gonna be the MA time, reciprocity and receptor exposure, which y'all have already done those. Those were due long before the storm came, I believe. Yes. And then so the things that were due Sunday week ago, technically, but really weren't, are distance, inverse square law, and the inverse square law math. So there was 3 of them. So those are the only 3 that you probably have not done, may have done, but may not have done yet. And so I'm going to finish working on getting this resorted and dates fixed and all of that when I go back downstairs after this. And so I'll send that, I'll get that out to you
Yesterday.
We'll figure it out. We've been through crazy stuff like this before.
I was looking at the review questions and it asked what a breathing technique was, and like I do get like kind of what it is, but like if it asks what it is on the test, what exactly what was.
So her question is, what is the breathing technique? And so a breathing technique means you are setting a manual MA in time with the MA being very low and the time being very long. And that is so that you can take advantage of motion to blur ribs and lung markings on things like sternums, areosternums, lateral T-spines, transthoracic humerus. So if you are trying to figure out what a breathing technique would look like, it's going to have a very super low MA and a very long time, which goes against what we typically do, right? Typically, we want a very short time to prevent the patient from moving, but that is just one way that we can actually take advantage of motion? Does that answer your question? Okay, any other questions?
How many questions are there?
It's always around 30-ish. I can't, sometimes it's 28, sometimes it's 32, but most of the time it's around 30-ish. I can't remember exactly. Yes.
Will you be posting your review questions and answers?
I thought I already did. I didn't?
No.
Okay, yeah, I can definitely do that. For sure. Yeah. Anything else? Thank you for reminding me. Okay, so, let me stop this recording. It's gonna be so long.